All right. Good afternoon, everyone. I think we'll get started here.
Sorry, one second. Look at
Okay.
me.
Just a second.
Oh, Professor, could you speak if you can?
I'm sorry. I'm having a little hard time.
It's coming through. Okay, I think we're good to go. Everybody's here.
All right. We're good to go. Okay. All right, everyone. Welcome to Tuesday. It's not much time left, and I think because of that, I'm going to probably skip the second lab that I had tentatively scheduled for Friday. I think we'll continue the 5G lecture. I think that'll be more beneficial for you in the long run. And so we'll have a lecture on orthogonal frequency domain multiplexing, maybe finish up MIMO today, OFDM, and 5G, probably carry over a little bit on 5G and cellular telephone systems in general on Friday, and then we'll think we'll have one more week after this, if my schedule is correct. Yes. So next Tuesday we'll talk about standards and research directions. Just talk about the various standards and how communication systems are developed and designed and standardized and stuff. And then we'll have a review on a week from Friday. And then I think our final exam is scheduled for May 9th. Yeah, wow, time's flown by. So I will started thinking about what's going to be on the final, and the finals I think worth 25% of your grade. So it's a great chance to bring your grade up. Hopefully it doesn't bring your grade down, right? So I'm gonna try to release some sort of preview on this week, later this week, about what the final will be. But for now, you can expect it to be similar to the exams we've had so far, and also the homework. And so, yeah, hopefully you can start looking at things. I know things get really crazy. A few of y'all have some travel planned for your capstone projects and stuff, so that sounds really exciting. And if there's conflict, I know there's some conflict already I'm starting to address, but if there's more time conflicts with the final, let me know as soon as possible. But yeah, your capstone's probably going to consume a lot of your time, so I encourage you to be looking at this course early and continually as we go over the next few weeks, so that you're not trying to cram on the last one. Hopefully I'm telling you just obvious stuff that you guys have learned how to study by the time you're seniors, but I think it's worth saying. So all right, let's get going with
Professor, we have a question.
yeah.
What time is the final? Is it the same?
11 to 1.
I believe
Okay, that was just a question with the final, but that
yeah, 11 to 1 on May 9th. That's what I put up in the final schedule a while back. Semester, I'll confirm that. But yeah, expect it to be a 2 hour exam. Okay, all right, let's dive in then. And yeah, so here's our schedule. I guess today's the 25th. April has flown by for me. So OFDM 5G. And instead of this lab on radio, we'll just continue looking at 5G. I don't think we'll finish the lecture today. So all right, let me go back and so we looked at the idea of multiple antennas, and we looked at a single input or single transmitter and multiple outputs or receivers, and how we can transmit using one antenna but have multiple antennas. These are, usually spaced on the order of wavelengths away from each other, but generally you don't have the space to do lots of wavelengths in terms of separation. And we linearly combine these, and so this can be a number of antennas. Typically it's 2 to 4, can be a little bit more than that, but typically it's 2 or 4 antennas. We combine those and we can get some gain out of it. If at the receiver we tell the transmitter what the channel looks like, then the transmitter can actually kind of pre-code it or compensate for the channel differences, all these different reflections and paths and that type of thing, at the transmitter using multiple antennas. And then the receiver can use a single antenna. Then we looked at single user MIMO, where now we have multiple input or transmit antennas and multiple output or receive antennas, and where we do both a little pre-coding and combining. And now we can have up to R different streams. In some cases, we can use those streams if we have really good signal noise ratio and we're not experiencing that many errors. Then we can take like half our bits and send it on stream 1, and the other half of the bits or symbols and send it on stream 2, or however many streams you have. And so you can gain some throughput that way. Or you can set up the different streams to include some redundant information and essentially do some error control coding via these different streams. And, a simplistic way of doing it is just maybe send the same information on all your streams, and a receiver picks the best stream and processes that. But there's more sophisticated ways of doing this. Of course, as a lot of these topics are, there's lots more depth to them that we could go into, but we don't have the time. It's really more for a graduate level course. So
We have a question.
Yeah.
Professor, did you say that when you say input you mean transmitter, and when you say output you mean receiver?
Yeah. So I guess it's relative to the channel. So if you can think of it that way, if the channel is between the antennas here, you have multiple inputs into the channel from your transmitter and multiple outputs from the channel for your receiver. Okay, so it's not really a factor on the MIMO, but for like the MISO, you've got multiple inputs into the channel and one output. And likewise on the CMO, a single input into the channel and multiple outputs from the channel.
Okay, thank you.
Okay, so we have both single user MIMO, and then we also have multi-user MIMO. This is a little bit trickier because here in the single user MIMO, in the receiver, that's at a particular location. All this transmitter, let's say the transmitter is the uplink in this case, and so this would be the handheld unit or the subscriber unit, we often call it SU, and this would be the base station. And but there's just one user talking to one base station, so all this processing can occur at one location, right? All this processing occurs at one location, or vice versa for the downlink. If this is the base station transmitting to the subscriber unit, your cell phone, then all this processing occurs at one place. That's not the case with multiple access or MU MIMO type situation. Here we have on the uplink from subscriber units to the base station, we would have these isolated, distributed phones or computers or whatever, right? Subscriber units. And they're operating independently. They've got their own processor and stuff. And so they don't really know what the other users are doing. So there's no real chance of joint optimization there. So each one's doing its own thing. And here on the base station, though, all this is in common, but we need to extract out the different users and all. So there's some interesting ways of approaching this, and the general approach is called multi-user detection at this location here, and it's using this idea of a successive interference canceller. Essentially what it's doing, and I'm just going to give you a high level description, is that it starts with trying to decode or extract out one of the users. Typically it's going to start with the strongest one, right? Strongest signal. And it's going to try to isolate and extract that signal. Once it does, then it subtracts that estimated signal from the composite signal. And so now if you have n users you're dealing with, once you subtract out that first user signal, now you really have n minus 1 signals in that composite signal. Then you do it again and you subtract out another one. You isolate it, you estimate it, then you subtract it out from that composite signal. Now you have n minus 2 signals left to process. So you continuously do this, and there's a lot of exotic math involved here, but basically you're trying to progress through and extract all of them out. Instead of simultaneously, you're kind of doing it one after another. There's lots of tricks, of course, as you get down to that last one. Any errors that you started with have built up, and you might have a lot of problems. So there's a lot of exotic type approaches in that. So maybe, like, you know, I hope you can maybe understand the idea of this multi-user detection successive interference canceller. If you know, you're talking about this in an interview, let's say, and someone asks you, how do you do this, or can you describe multi-user detection, or I ask about that on the phone, then the idea is that you're making a best estimate based upon the strongest signal. You're subtracting that from the composite and iterating through the process. You might then kind of go back and do that over and over again to try to improve your estimates. But, you know, that's diving down into the guts of the algorithm, and we're not going to cover that. But understanding the concept in that you have multiple users all blended together in this composite signal, but you try to use the information you have, and you do this kind of joint demodulation decoding in an iterative process is a good thing to know. One of the keys to this is that you know, some users are going to be real close to the base station and others are going to be far away. And those that are far away not only have a smaller signal, they have more propagation loss by the time they get to the base station, but their signal is also delayed. And a lot of this processing is assuming that all these signals are aligned in time. So, we can achieve this in a couple of ways, right? So we can say, all right, let's group all the radios that are near us, near the base station together, and instruct them to communicate together. And then we'll group those that are far away from us and instruct them to also communicate together. And we can also instruct some to slightly delay their transmissions, or and so ultimately at the receiver, your various users that are combining in a channel to into one composite signal, that they're aligned in time, either by selecting in that way so that they're all approximately the same distance away. It's non-trivial, right? So we don't know exactly where these radios are, but we can estimate it, right? And we can also instruct, if we notice that a radio's signal is arriving so many nanoseconds after another signal, then we can instruct one to delay or one to advance their transmission to get things lined up. But that's a challenge in this multiple access channel here that we're dealing with. All right, then we have the broadcast channel. Now this is the downlink, and now the base station is sending out its information, and it's combined data for all of the different subscriber units out there. Maybe someone's watching a video, another subscriber unit's involved in just browsing some email, and another one is on a voice call or video call or something, right? So they all have distinct data streams going to them, and the base station will combine those data streams, and it has to tell the subscriber unit, hey, these are your packets, and ignore the other ones. There's obviously a lot of security involved there that at higher levels of the network stack. But again, using this MIMO type situation, we are going to pre-code these signals here and downlink those to the different users. Here we call it dirty paper coding. It's essentially a very similar type of thing. We're trying to allocate these streams and stuff to different users so that they're easy to isolate here at the receiver. Not going to go into the details of the algorithm. But here the transmitter, the base station, can handle all the timing control itself, and these guys are just trying to isolate their own signal, and they're throwing away the other signals, so we're not having to do that successive interference cancellation and that type of thing. So it's a little bit easier in terms of the timing control and group selection. Okay. All right. So that's what we, kind of breezed through at the end of last lecture. And so let's kind of pick up on that, continue a little bit with some very hand-wavy math, and then we'll dive in and look at 5G, and a lot of this we'll talk about it. 5G is also applied in more legacy 4G type situations like LTE and that type of thing. But we'll look at specifically 5G issues and look at the physical waveform that's used there. So, all right, so we talked about SIMO, MISO, MIMO, whatever, MIMO. Let's start back with the baseline. It's a single input, single output, right? And that's what we spent most of the semester talking about is single antenna type system on both transmit and receiver. And we know that at the receiver, we're going to get a signal X, and it's going to be composed of the transmitted symbol times the channel effect, okay, the channel, and plus noise, right? And the in the case of a maximal likelihood type of a receiver or match filter type of receiver or whatever, we're going to use the complex conjugate of the channel response, and this gives us our metrics that we're going to be able to estimate the true symbols sent, right? And so this is just kind of some math that describes that process. And then we have this Shannon's capacity theorem that has our power scaled by the channel and the noise, the variance of the Gaussian process for AWGN type channel. There's a bandwidth out here, but we're not carrying that through because that's we're assuming a fixed bandwidth type comparison here. So, and so this is why it's bits per second scaled by hertz there. So now let's look. What do we do in the case of this single input, multiple output? Our receivers now dealing with vectors, so we do get a set of symbols sent, and it's those symbols are modified by the various channels that we have, right? So we might have a direct path, we might have one that reflects off a wall, one that reflects off the floor, ceiling, the other wall. We showed some of those pictures last time, right? And so there's multiple channels to get to the receiver. And so how do we do this? Well, we do a similar process, except now it's a vector. So when we do the complex conjugate, we talked about a Hermitian. So here we're scaling the sent symbols with the norm of H and the noise also by this Hermitian of H. And so now we can look at this and we see in here there's slightly, ever so slightly difference there, right? So we've got this double bar here, right? Double vertical bar instead of the simple absolute value here, right? And so this is how we are looking at a vector, right? Where we're squaring each of the elements and adding them up. And so now we have this power gain due to the multiple channels. So if each of these individual channels, we'll just assume they're lossless one, right? It's unrealistic, but include the transmitter power amplifier and a receiver amplifier, maybe it's one, right? But now we have n of them. And so if they're all equal and we have n of them, then this norm of h squared is going to equal n. So, I don't know if you can hear it. My dog is coughing in the background. So he's been sick. All right. So that gives us some gain. So we're going to have a capacity increase over the single antenna type situation, as you might expect, right? You have more antennas, hopefully we're going to get something out of that, right? Now let's look at this MISO type situation. Here we're kind of pre-coding it. So we're doing this processing at the transmitter, right? So kind of doing this match filtering process. And I know I'm doing a lot of hand waving here, but this match filtering process at the transmitter, we're pre-coding it so that then when we get to the receiver, everything is all lined up for us, right? So now, if we look carefully, we see here that this channel here is Hermitian of the channel response is multiplying your noise vector, but here it's not because all that processing has been done at the transmitter, and the noise shows up in the receiver, right? So we're not multiplying it there. So we can get a little bit of a gain there. By pre-coding, we're avoiding amplifying the noise with the channel gain at the receiver. Now with MIMO, the system uses a combination of pre-coding and linear combining, right? So we have multiple antennas at the transmitter, and we're pre-coding it. So we're sending some version of the signal on antenna 1, a little different version of the signal on antenna 2, and so on, right? And so now we can, then also on the receiver, we're doing this linear combining also. So how do we do that? Well, it's going to be beyond the scope of what we can talk about in this course here, but you're basically taking that MIMO channel and decomposing it into R parallel. In other words, they're non-interfering scalar Gaussian subchannels. All right, so they're we're taking this vector and we're composing of individual scalar subchannels, each of which is a Gaussian type of distribution, right? So and in practical cases, our R is going to be 2 to 4 or something like that, right? So R is actually the rank of this H matrix, and for if you kind of remember back to your linear systems concepts, maybe you learned about that in math methods. For H to be full rank, then we're looking at a minimum of the dimensions here, m versus n. So then R is that. So if you have more than that, it's there's some redundancy and stuff, right? So all I'm just going to say is that the pre-coding matrix is then derived from an Eichen decomposition of this H Hermitian times H, and likewise the linear combining matrix is derived from H times H Hermitian. So we're decomposing these into Eichen values and stuff. So so we're not again going to go into it much more than that, but that's the high level concepts there. So multiple antennas really are only going to be useful when you have independent channels that you can isolate, right? Now, out there in the ether and the free space, then signals are going to combine. They're not really rays, but we approximate them as rays, that type of thing, right? But we know that these waves tend to reflect off of objects, and they obey Snell's law when they do that. And so only certain reflections end up directed at the receiver antenna, right? So others might reflect and go off into oblivion or somewhere else, right? So you're getting a finite set. We talk about, when we draw our diagrams, there's a few rays. There's actually many of these things, but it's still a limited set, right? So how does this whole process work? Well, the receiver estimates the channel from known sounding signals sent by the transmitter. So the transmitter is part of the waveform, the part of the standard. It's going to quasi-periodically send some known signals, known amplitude, known phase, known modulation type thing. And the receiver is going to receive those and measure it, right? It's going to measure the amplitude, measure the phase. And if you send one of those symbols and the receiver actually sees about 5 of them, then it knows that there's 5 different rays that are reaching that receiver through various different paths, and it can measure the delays of those and that type of thing, right? So it sends this information to the transmitter as this channel state information, this CSI, okay? And that, again, is described in the standard how to encode that information. And so then we can do these inversions or eigenvalue decompositions and that type of thing. But if all these rays are too similar to each other in terms of amplitude, in terms of phase, delay, that type of thing, then this whole process can get buried in the noise and in the numerical challenges of doing some of these matrix inversions and that type of thing, right? So and we can't really produce a matrix that is able to separate out these signals effectively. So I know that's again a lot of hand waving, but once you understand kind of the concept, so if the propagation environment is too clean, then all these signals look too similar to each other and they're too hard to separate out. Okay, so that's the key kind of thing to understand there.
Professor?
Yeah. Go ahead.
Yeah.
So when we're talking about like multipath, are the same multiple paths generally repeated, or is it like random so that even if it does something like this where it tries to measure, won't there be differences in multipath?
That's a great point. So this whole process of sounding the channel, the receiver measuring it, sending the transmitter that channel state information, assuming that it's a MISO or MIMO type situation where the transmitter is doing pre-coding. That has to be done while the channel is quasi-static. Because if you're moving, which we typically are, then that channel is changing constantly. So this is a continual process that has to be done periodically, and it's only valid for a certain amount of time. And yeah, as you can imagine, as you move, then these multipaths, the ones that actually reach the receiver, are changing quite a lot, right? So yes, a very good point in that. So the whole process has to go through. Then you actually send the data, and by now you've moved, and that channel state information is no longer valid. So you need to repeat the process again and again and again. And so that's why communication standards, also delay issues and Doppler issues in particular, they all place some bounds on how fast things can be moving, and the communication systems still keep up, right? So if you try to put a 5G radio on, let's say, a hypersonic missile to communicate with it, it's not going to work, right? So because all of this is assuming that there's some upper bound on how fast things are moving relative to each other and how fast that channel is changing. So you remember back in your sophomore year, somewhere along the line you made these assumptions about a linear time invariant system, and all your early work was all based upon LTI, linear, so you can use superposition, and time invariant. So yeah, you don't have to worry about what time you're actually doing these calculations, right? We're no longer in a time invariant system, but we're still breaking it up. Just like if you had a very nonlinear system, you kind of break it up into a piecewise linear approximation, and you say, well, if I look at this amplifier over this narrow range of input amplitudes, then I can kind of assume that it's linear over that tiny little range. And then well, if I have a different input level, then I'll make a different piecewise linear approximation. So we're doing the same thing in the time domain, in that we're assuming that things are fixed over some very short period of time. Even though the channel itself is time varying, we're going to assume it's time invariant over some short period of time. So very good point. All right, I'm about out of time on this Zoom session, so I'm gonna stop it here, and we will pick up on the next Zoom here momentarily.